So we're now going to talk about how to combine old statements to create new ones. So you can create a new statement out of old statements by applying logical operations to the old statements. So we're going to talk about some logical operations. First one is and. Given statements P and Q, okay, two statements there, the new statement P and Q, which is denoted like this, is true whenever both P and Q are true. Otherwise, it is false. Here's an example. Suppose that E of X is the open sentence that X is even, and I of X stands for X is an integer. So here's an example using and. So E of 10, that's a statement by itself. E of 10 is a statement. It's a true statement. I of 14 is a statement by itself. It's also a true statement. Putting them together with and creates a new statement. E of 10 and I of 14. So 10 is even and 14 is an integer. This new statement is a true statement because both of them are true. Remember, P and Q is true whenever both P and Q are true. Suppose we have this. Suppose we say that 10 is even and 1.4 is an integer. So 10 is even is true. 1.4 as an integer is false. Putting them together with and makes this a false statement. So the only way for and to be true is when both halves are true, both parts are true. Another example, let's say we say E of 9 and I of 14. So E of 9 is false, right, because 9 is not even. I of 14 is true, but this new statement is a false statement. And finally, if we say E of 9 and I of 1.4, meaning 9 is even and 1.4 is an integer, here both of them are false, so this is certainly a false statement. Now for logical operations, we're going to use something called truth tables. So here's our first truth table for P and Q. So we're going to want to do a truth table for the statement P and Q, and P could be anything and Q could be anything, any logical statement, and Q could be any logical statement. And we're going to do P and Q. So we first set up the table. So we're going to have we're going to have one column for P, one column for Q, and then a column for the result, P and Q. Now, what we want to do is try to find all possible combinations of values for P and Q. In other words, P could be true or false. Q could be true or false. How many possible combinations are there in total? Well, if you remember counting, hopefully you'll remember that this is, hopefully you'll realize that this is 4, right? 2 to the power of 2. You have 2 choices for P, 2 choices for Q. The total number of choices is 4. So we have to make sure we cover all possibilities. In other words, all possible combinations of true or false for P and for Q. So the way we ensure that we cover all possibilities, well, the way I do it and the way the book does it is as follows. So we start with the rightmost one here, meaning P and Q. We start with doing Q. We could start with P, but the convention is to start from Q. And we write true, false, true, false. So alternating true and false, true and false. Then we do for P, we do something similar, but not exactly the same thing. For P, what we do is we do groups of 2. We do true, true, false, false. Now, if you look through these 4 lines, TT, TF, FT, and FF, these cover all possible combinations of truth values that are assigned to P and Q. Now, what we have to do is fill out the column for P and Q. In other words, what happens? So, for example, this first item here will tell me what happens when P is true and Q is true. What will be the value of P and Q? And the answer is that will be true. And then the rest of these are false, right? So if P is true and Q is false, then P and Q is false. If P is false and Q is true, then the result of P and Q is false. If P is false and Q is false, then P and Q is false. Okay, so this is a truth table. And this is all about the AND operation. Here's another logical operation, which we call OR. And sometimes you might see it called inclusive OR, but the standard OR is inclusive OR. And I'll explain what I mean by inclusive OR in a second, because we're going to see that there's a different type of OR, which is called exclusive OR. Given statements P and Q, the new statement P or Q, which is denoted like this, P or Q, is true when at least one of P and Q is true. It is false only when both P and Q are false, meaning the only way for it to be false is if both of them are false. If either of them is true, or if both of them are true, then the result is true. So for example, as before, let E of X represent that X is even, I of X represents that X is an integer. So here we have a statement. Well, E of 10 is a statement saying that 10 is even. That's true. I of 14 is a statement saying that X is that 14 is an integer. That's also true. This new statement here, E of 10 or I of 14, this is a true statement because at least one of them is true. How about this? Well, here the first one is true, the second one is not true, but at least one of them is true, so it's a true statement. How about this? Well, here the first one is false, but the second one is true. So at least one of them is true. So this new statement is a true statement. How about this? Here, both parts are false. So here is the case where it is false. Here we're going to do a truth table for P or Q. So again, we're going to set up the table like this. We're going to put down our alternating true and falses for Q, and then the groups of 2 for P. And then we're going to figure out what is P or Q. So for the first one, it's going to be true, and then true, and then true, and then false, like this. Now we do XOR, or exclusive OR. Given statements P and Q, the new statement, PX or Q, which is denoted like this, it is true when exactly one of P and Q is true. Otherwise, it is false. So if both of them are true, if both of them are false, then it's false. If exactly one of the two is true, then PX or Q is true. For example, same as before. So here we have something that's true. 10 is even, that's true. 14 is an integer, that's also true. But this is exclusive OR. So we're saying E of 10 X or I of 14. So this is false. It's a false statement. Here we have one that's true. The first is true and the second is false. So this is a true statement. Here we have the first one is false, the second is true. This is a true statement. Here we have both of them false. This is a false statement. Now we're going to do the truth table for P, X, or Q. So again, filling in alternating true, true, and false, then groups of 2, true and false, and here are the results. Note the difference between OR and XOR is in this first part of the example, right? For if this would be a plain standard OR or inclusive OR, then this would be a true statement, right? Inclusive OR includes this. Exclusive OR excludes this. Okay, so that's why, so the standard OR is inclusive OR. Exclusive OR is XOR. Now in English, English is more difficult than math. You'll see, and in English, there are a few different ways to express P, X, or Q. So in English, P, X, or Q can be expressed in any of the following ways. You might say the following: P or Q, but not both, right? So we're saying, so the word or typically just means inclusive OR. But if I want to express the idea of XOR, I can say something like P or Q, but not both. Or I might say something like this: exactly one of P and Q, meaning not both, but exactly one. Or you might say either P or Q, and that either kind of, well, often means that it has to be one or the other, but not both. This last thing here, this either, is not totally foolproof. In other words, you'll see sometimes people use the word either even when they mean inclusive or. So it doesn't always mean exclusive or, but it usually means exclusive or. But these first two are more clear, right? P or Q, but not both. That's pretty clear that we mean exclusive or. Now, it's a little problematic sometimes because, people often make statements of the form P or Q when they really mean P, X, or Q. Okay, and this comes up, in everyday conversation and sometimes even in mathematical contexts. So you have to be aware of the context of what's going on, or you could ask, for more information if you're not sure. You can often do that, but it's just, ideally, or just means inclusive or, and to say XOR, you would use one of these expressions. But sometimes people say just the word or, and they really mean something like XOR. So here's an example of that. So consider the sentence: the lunch special includes a free soup or a free salad. Right. So if you pay $10 for lunch, it comes with a free soup or a free salad. Right. So is this or inclusive or exclusive? Well, based on the context, they're giving you something free. Probably they're not willing to give you two free things, right? So even though they're just using the word or, and they're not saying but not both, they're just saying or, they probably really mean exclusive or, right? So the intended meaning likely is this: the lunch special includes either a free soup or a free salad, but not both. So that's something to keep in mind. So, or, typically or means inclusive or, but sometimes people use the word or when they really mean exclusive or, and often you can determine based on the context that they really mean exclusive or. Okay, but again, ideally, when you're writing and you want to express exclusive or, you should use something like P or Q, but not both. Okay, one more logical operation for this video: not, or negation. So given a statement P, the new statement not P, which is denoted like this, not P, this is true whenever P is false, and is false whenever P is true. For example, let E of X denote that X is even. So what about this? Not E of 4. So E of 4 means that 4 is even, right? So this is true, 4 is even. How about not E of 4? That means not 4 is even, or in other words, it is not true that 4 is even. That is a false statement because it is true that 4 is even. Okay. How about this? It is not true that 3 is even. That's true, right? It is not true that 3 is even. Here's a truth table for not P. So here we only have P to figure out, right? We only have the variable P to deal with. We don't have P and Q, we just P. So the only two possibilities for P are true and false. Those are only two possibilities. And so when P is true, the result, not P, is going to be false. When P is false, the result is going to be true. In other words, not P is going to be true. Now in English, something like not E of 3 can be expressed in any of the following ways. In other words, 3 is not even, not 3 is even can be expressed in any of the following ways. We can say in English, it is not true that 3 is even. Or you can say, it is false that 3 is even. Or you can say, the number 3 is not even, right? The reason for adding these two words is that it's not good grammar to start a sentence with a number. So just, in other words, it's not you want to start a sentence with words. That's just English, grammar or whatever. So, in other words, you don't want to start a sentence with the 3. Really, I could just say 3 is not even, right? But when you write English, in speech, it's fine to say 3 is not even. But in written English, typically you don't start a sentence with a digit or a numeral. Anyways, so that is one note, and another note is regarding order of operations, or not order of operations. Like let's say I have something like this: not P or Q. So what does it mean? In other words, does it mean does the not just apply to the P, or does it apply to the P or Q? In other words, do you have parentheses around the P or Q or not? So by default, not P or Q means this. It means not P or Q. It does not mean this. It does not mean not P or Q. That would not be correct. All right. The meaning of this is this. It's kind of like negative, negation. Like, let's say I say -3 + 5. Right? The negative is just being applied to the 3. It's not being applied to 3 + 5. It's just negative. Sorry, it's just -3 and then +5. So it's not P or Q.